So today's the last lesson, the 10th lesson of the summer session for this AMC class. After this, there won't be any more classes until a future session in the fall. And yeah, we'll send out more information about that later. Like if you want, if there will be a full session, and then we'll cover 6 more weeks of topics, different topics that we have not covered in the summer session. Uh, Anyways, on to the content. So today's topic is more counting strategies and stuff. Sorry, I just need to shut my door. So today we'll be going over more counting strategies such as stars and bars, also known as sticks and stones, as well as complementary counting, the latter of which comes off up a lot. Now first we'll go over some homework problems that were often missed. All right. So the first problem is there are 9 parking slots in front of the school for 6 teachers and the principal. If the principal always gets one of the 3 spots closest to the door, how many ways can all 7 cars be parked? Okay, so this one I admit was kind of ambiguous because they didn't say whether or not the teachers should be counted as distinct. In this case, they are distinct, but yeah, sorry about that. Next time we'll specify, we'll make that clear, okay? So I'll just go over this one quickly. So let's say there are like 9 spots. Let's say these 3 are the ones closest to the door. So we know the principal has to park in one of these. So we take, as I believe I said last class, we take care of like the most restrictive things in accounting problem first, that being the principal in this case. So the principal has 3 spaces to park. For the rest of the 6 teachers, there are 8 spots left, and there are 6 teachers to fill them. So the answer would be P of 8, 6, as you can like multiply out 8 times 7 times 6 times 5. And check that to see that it is indeed P86. And that should be, I believe, 6840. Correct me if I'm wrong on that. If the teachers weren't distinct, then this would just be 3 times 8, choose 6 instead, giving an answer of 84. So yeah, I did see 84 a couple of times. So sorry if you got that and it didn't get marked as right. We will make sure not to do that next time. All right. Sorry, this should be 6480 actually, not 6840. I believe. So yeah, that's the right answer. And that's how you do it. Remember, for this problem, I guess the main takeaway is always account for the most restrictive possibilities first when doing something, when doing like counting like this. Similar problems include like, let's say they say the units digit of a number has to be even or something like that. You take care of that first. And for this one, how many ways are there for get from the bottom left square, not the point to the top right square, going only up or right? All right, so for this one, the moves are like this. And we see that there are 7 horizontal moves, 4 vertical moves. So as I believe I mentioned in last class, the way you do this is it's just like arranging left, 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 where there's 7 L's, right, 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 where there are 4 R's. It's just like arranging this, and that's just 7 factorial over 4 factorial, no, sorry, 11 factorial over 4 factorial times 7 factorial. Why is this? Because, well, for each arrangement of this, it gives a unique, distinct sequences of moves that you can like trace out and follow to get to the end. You can also choose it as all. There are 11 slots for moves, and you want to choose, let's say, 7 of them to be horizontal, or equivalently, you can choose 4 of them to be vertical. And of course, as you probably know, those are the same quantity. You want to evaluate that really quick. And we get rid of the 7 factorial first, leaving us with this. Times 8. 24, which is 4 factorial. This is 3. So then the answer should be 330. All right. Yeah, sorry. 4 R's, not 4. No, 4 U's, not 4 R's. By R, I meant like going up. Sorry if that wasn't clear. Oh yeah, anyways, that's how you do the homework. So we'll move on to today's class content. For complementary counting, the concept is simple. You find the total number of outcomes, subtract the ones you don't want. In many problems, this will be easier than counting directly. I feel like you should actually do this example first because it's simpler than this one, at least in my opinion. But yeah, I'll go ahead and do these with complementary counting, meaning you count what you don't want, or like, yeah, what's the opposite of this? A and B don't pass a path from A and B doesn't pass through X. The complement is it does pass through X. Then you subtract that from the total number of paths, right? So yeah, that's just complementary counting. So yeah, quickly, you can go ahead and work out these two problems and see what the answer is. Many times the tip off to use complementary counting is just like at least, or some like, yeah, some similar expression at least, although this is not always the case. Sometimes this will also involve principle of inclusion exclusion, although you'll learn that later. When probably if you go on to take the AMC 10, you'll hear about it more. Yeah, anyways, just do these examples first. And you can chat me or the TA your answer when you're done. All right, I'll go over these now since I've seen enough correct answers. So does anybody want to go over this? Anybody who got these right? Just raise your hand if you want to. Right, I guess not, so I'll just go over both myself. For the first one, so if we count the paths that pass through X, so how many ways are there to get from A to X? Okay, well, we know on the whole, there are 10 unit, it's a 10 unit path. There's 6 moves this way, 4 moves this way, so we can't afford to go down or to the left. So thus we know that we can only move up and to the right throughout. So just like the path problems mentioned before, going from A to X up and to the right only, this four choose 2 ways, because a total of 4 moves, they choose 2 to be horizontal or vertical in this case. Similarly, from X to B, there's a total of 6 moves, and 6 choose 2 or 6 choose 4, they're the same. And this is our complement, this is what we don't want. So this is equal to 6 times 15 is equal to 90. And the total from A to B is just 10 moves total, choose 4, or 10 to 6. We calculate that. That should be 210, as you see here. So 210 minus 90 is thus 120 paths, which I do believe I got an answer for from someone. And this is actually like, yeah, this is not too bad for complementary counting. Sometimes you'll have to watch out for other things as well, but yeah. So it's pretty simple. How many paths don't pass through X? Well, you count the number that pass through X and subtract it from the total number of paths. And so now I'll go over the second problem, having said that. So this one I actually got a bit of like small errors from some people. So first off, I think most people got the total right. Each flip can be head or tails, there are 8 of them. So there are 2 to the 8th is equal to 256 total flips. Total, I mean ways to like get flips. How many ways can you flip at least 2 heads? Okay, so if he flips 1 head, right? That's one part of the complement. So there's 8 choose 1 ways to choose one that's a head. And that's it. Pretty simple. If there are no heads, they're all tails. There's only one way for that, 8 tails. So it's 256 minus parentheses 8 plus 1 is equal to 247 ways to flip at least 2 heads. This is the complement and this is the total. In this case, the complement has multiple parts you need to consider. So yeah, I guess that what might be what threw people off a bit here. But yeah, do be sure to account for 0 heads as well as 1 heads. And we'll see more like and oftentimes complementary counting won't be just as simple as this example where there aren't multiple cases you have to consider as the complement. And a rule of thumb is like if counting the complement takes more work than counting it directly, don't use complementary counting. But in these cases, definitely complementary counting is better than not. And just to recap of combinations, some problems we didn't get to last time. So a fair coin is flipped 10 times. How many ways are there to flip more heads than tails? And then the easier one, how many different sets of 3 books can be chosen from a set of 20? All right, for this problem, so there are a couple of cases you can consider. So we know the total, just like before, is 2 to the 10. I'm pretty sure most people got that. Now there are 3 cases when the amount of heads is greater than the amount of tails. The amount of heads is equal to the amount of tails, and then the amount of heads is less than the amount of tails. Now try to connect these two, see what the relationship between these two quantities is. Think about what happens when you change every flip that's a head to flip that's a tail, basically reversing every flip, and every flip that's a tail to head. Think about what happens when you do that and try to relate these two. And then yeah, just use that. I think I've said enough, gave away enough, and then use that to find how many ways are there to flip more heads and tails. This should be just straightforward application of combination. So I'll give everybody like I don't know, maybe 5 minutes to do these. All right, for the second problem, just to be clear, we're talking about sets of 3 books. So we mean that like the order of the books within that set of 3 doesn't matter. Just in case some people didn't get that. So again, for the second one, order does not matter. All right, so let's go over these. Does anybody want to show how they did either one?
I want to.
All right, yeah, sure, go ahead.
The second question. So what I start by doing is since we first start seeing that order matters, then divided by six 3 factorial, because the order doesn't really matter. So we start off by 20 factorial divided by 17 factorial times, divided by 3 factorial, since the order doesn't matter. So it's 20 factorial divided by 17 factorial times 3 factorial, which is 18 times 19 times 20 divided by 6, which is 3 times 19 times 20, which the answer is 1140.
Yeah, that's right. So yeah, this is it's just 20 factorial over 17 factorial times 3 factorial. Honestly, the way he went through it is basically derivation of the formula for 22(3), which is just 20 factorial over 3 factorial times 20 minus 3 factorial. So yeah, that's basically how you do it. Because the ordering of the book within itself doesn't matter. That's where the 3 factorial comes from. Right. So I hope that's pretty clear. This should have been straightforward. Let's see. Does anybody want to present the first problem? Sure. Wang Guo, are you raising your hand?
Oh wait, sorry, let me name myself first. Okay, so we can look for the number of ways where heads is equals to tails. So we have 10 choose 5. So 10 factorial over 5 factorial squared. So let me, and then subtracting this from 1024, you get 776. Okay. So 1024 minus equals 776. Oh wait, sorry, it's 772.
Yeah, that's right.
Then-
All right.
And then you divide by 2 because the number of where it's more heads is the equal number of more tails. So you get 386.
All right. Yeah, that's right. So that's how you do it. Well, if we didn't really get what the process was behind this, first thing you notice is that the amount of ways for heads to be less than tails is equal to the amount of ways for heads to be greater than tails. Why is this? Because if you just like flip in each way such that a heads is each possible sequence of flips such that the heads number is less than tails, if you replace each head with a tail, each tail with a head, you get one where the heads is greater than the tails. So all you need to do is subtract the number where the heads are equal and then divide by 2 to get the answer. And that, as you know, is 10 choose 5 is 10 factorial over 5 factorial squared. So you subtract it from 2 to the 10, that's twice the number you're looking for. So then you divide by 2. And yeah, 10 choose 5 is actually not that hard to calculate, although it's somewhat intimidating. As you can see, it's over 120, and this is 6 times 7 times 6, 252. Oh yeah, another example of complementary counting. This one required a bit more thought than the other ones did, I'd say. So yeah. So stars and bars are sticks and stones. So stars and bars is a very useful trick in counting that allows you to represent participations in combinations with combinations. It's better explained with this example. Uncle Henry has 10 $1 bills to distribute to 5 nieces and nephews. How many ways does he have to distribute them? He must give each of his nieces and nephews at least one bill. So each one gets at least one. Although right after this, we'll cover how to do it. If he doesn't have to give everyone one bill. All right. So the way to do this is, let's say you draw the 10 bills is like represented by dots. So in each of these gaps, of which you can count, sorry. So in each of these gaps, which you can count, there should be 11. In each gap, if every kid is allowed one, then in each of these gaps you choose like, so which gaps are valid? This one, 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 and this one. So that would make a total of, I believe, 9 valid gaps. And you choose 4 of them to be like dividing lines between the different people getting candy, so you can tell who's who. All right, yeah, anyway, so that would be how many gaps are there? 9, choose 4. Although actually I realized that yeah, never mind. So this is the basic premise of stars and bars, how to do it, how it works. A good exercise would probably be doing it if they're not if niece and nephew don't have to get one, all get one, and in that case, you have to think about like changing that into the problem where every niece and nephew gets at least one. And so yeah, thinking about how to do that would be a good idea.
So do they mean that there's 5 nieces and 5 nephews, or in total 5?
In total, there's 5. Yeah, sorry, that was unclear. Yeah, it's a total of 5 nieces and nephews. All right, so go ahead and do this problem, except he doesn't have to give every niece and nephew at least one. He can like be stingy and not give some of them anything. And as I said before, think about how you turn that problem into this problem, where each of the 5 total nieces and nephews has to get at least one. And sorry if I didn't explain this that clearly, but I'll just go over it again. So you choose 4 of these, like 9 places in between as your dividers. So let's say you choose these. So then all the stuff in between would be what each person gets. Since there are 4 dividers, you should end up with 5 sets of candy. Let's see, there are 2 here, 1 here, 2 here, kind of bad drawing, 1 here, and then this one gets 4. So yeah, that's how it works, and that's why you can't have any of the n divisors, because then that would allot someone 0. But yeah, just think about how to do it if he doesn't have to give every niece and nephew at least one, and send me your answer when you're done.
I have a question.
Yeah, sure, go ahead.
Like, can you be stingy and give none of the money?
I heard give him none of the money. Can you repeat that again?
What?
Can you repeat that again? I didn't catch the entire question.
Can you be stingy and give none of them money? Like, just
Oh no, I get what you mean. Like the total that you give to like them still has to be 10. Like that's not gonna change. But like you can give one cousin all of the $10, and like all of the other 4 0 is what I mean. Like the total is still 10.
But you said you must give at least 1 to each, right?
Yeah, that was for the example. Now I'm asking how many ways are there for him to give a total of 10, except he doesn't have to give 1 to each. Sorry if that was unclear. All right, so yeah, you can just send me your answer when you're done with that. To be clear, the answer you're sending me should be when not necessary when he doesn't have to give at least 1 to each.
What problem are we doing? Like the example?
We're doing the example, except he does not have to give everybody at least $1, but he still distributes a total of $10.
Okay, so there are 5 nieces and 5 nephews.
A total of 5 nieces and nephews. I think I mentioned that earlier.
Oh, so total of 5.
Yeah, total of 5. And just as like a quick check, the answer to this example, where everyone gets at least 1, is 9 choose 4. So your answer should be bigger than that, since there are more ways.
Does order matter? Does order matter?
Yeah, like if you mean if one cousin gets, I don't know, 1, the other one gets 2, next one gets 3, and the last one gets 4. This is different from like 3, the first one. There are only 4 cousins. I'm just using this as an example in this case. But yeah, this should be counted as different from this. Actually, yeah, I can just do that. Make it match the problem. So yeah, these 2 should be counted as different. So yeah, treat the cousins as different people. I mean nephews and nieces, sorry. Okay, so just to know, I've seen like multiple answers that are like a 3,000 or above. The answer is smaller than that. And okay, let me just write this here to make it clear. So the total he gives out 10 is $10. That's never gonna change. But not everyone must get something. Sorry. So I think that should clear up any like errors or misunderstandings. All right, this seems to be pretty difficult, but I'll give everybody like a couple more minutes. See if anybody gets it. So I'll go over the example first. I think some people may have not gotten the original case. So I'll try to be clear and reiterate it. So for this problem where everybody gets at least one, why is it 9 choose 4? So as I said before, there are 10 bills. And you want to put 4 dividers somewhere in like the space in these spaces between those. And what would that do? If you place 4 dividers, let's just arbitrarily draw them to like illustrate. Then you have 5, I guess, piles or groups of coins. And these are thus the groups of coins that the coins that people get. Okay. So yeah, and you can't put like any of the dividers at the end because like let's say you did do that. Then to the left of it there's nothing, which means the person gets 0. That's not allowed. Okay. So yeah, this is why it's 9 choose 4, because there are 10 objects. There are 9 spaces between them. Remember, we cannot have any of the ends as dividers. And so yeah, that's how it is. So that's why it's 9 choose 4, because you want to choose 4 among the 9 dividers in between. This one is 9 choose 4. I hope everybody understands that. And if you don't, you can ask me questions on why. Note that if not everyone gets at least 1, it's not simply like, so I'll erase this. So at first glance, if not everybody has to get at least 1, it seems to be a lot more complicated. Why? Because you have to guarantee the total is 10, but like you don't have to give everybody 1, so you can have like multiple dividers stacked, and it seems pretty confusing at first. But the way you do it is you since that problem isn't easy, you try to shape it into a problem where everybody gets at least 1. Well, to do this, you interpret it differently. So the original problem is just like saying the number of ways a plus b plus c plus d plus e is equal to 10. All of these are positive integers. All right, and like, yeah, the order of the so it's like ordered quintuplets, A, B, C, D, and E. Okay, so then this is an equivalent problem. The answer is also 9 choose 4. Simple enough. But what if we have like where a plus b plus c plus d plus e are not necessarily positive? Then that's equivalent to the second problem I asked, which is when the total is still 10, but not everybody has to get at least 1. And each of these represent and we're treating each of these variables as the amount each niece/nephew gets. So how do we turn this into that problem that looks like everybody has to get at least 1? Well, we add 1 to each variable. It's a plus 1 plus b plus 1 plus c plus 1 d plus 1 plus e plus 1 is equal to 15. Now, treating a plus 1, b plus 1, c plus 1, d plus 1, e plus 1 as the variables here, we see that they have to be positive. They can be any number that like works. And the sum is 15. So this will just be, by similar logic as to this problem, 15 minus 1 choose 4. I hope everybody sees why like you can do this manipulation, and it's basically treating a plus 1, b plus 1, c plus 1, d plus 1, and e plus 1 as like the variables in this new problem. So the answer is 14 choose 4, and I think that should be 1001 if I'm not mistaken. So yeah, that's how you'll actually especially in higher levels, you'll see this kind of problem often, and you should always like try to turn it into one where it's the sum of some positive integers is equal to total. And yeah, that's how you do it. There are like other problems, stars and bars problems that require more manipulation, but yeah. I hope everybody understands this. And if you have any questions, you can just ask about how I got there.
Why did you do 15 minus 1 choose 4 instead of 15 choose 4?
Oh, for that, if you go back to how we derived it, right? So what if they're like n things? Okay, I'll just draw the original 10. So we want to pick from these 9 gaps in between. We can't pick anything on the end because then what's to the left of here? Nothing. So then this person gets nothing. And then similarly for the rightmost divider. What's to the right of this? Nothing. So,
Wait, I mean for the example.
yeah, for the example. Yeah, that is what I'm discussing. And so this is why the example's answer is 9 choose 4. But it's the exact same thing for the sum of positive integers being 15. It's just that the number of objects changed. For 15 objects, there are 14 gaps, so that's why it's 14 choose 4 or 15 minus 1 choose 4.
Isn't there 16 gaps in the problem because they can get less than 1, which is just 0?
No, because we changed it to a problem where when we got to 15, we already like transformed it into a thing where everybody has to get at least 1.
Oh, okay.
Yeah. So yeah, I think that should clear up everything, almost everything. So some more variants. Stars and bars is placing dividers to separate items in the categories, like I illustrated in the last slide. Use combinations to choose where the bars go. Sometimes you need to modify the concept by removing some stars or with complementary counting. So how many ways are there to roll a sum of 7 with 3 6-sided dice? How many ways are there to roll a sum of 13 with 3 10-sided dice? All right, so the restriction, so this one, obviously dice are like positive integer sided things, 1 to 6 and 1 to 10. The thing you need to watch out for is if you have, say, a plus, for the first one, a plus b plus c equals 7, you can't have any, none of these variables can be more than 6. And they're dice, so they have to be positive too. So yeah, just go ahead and do these actually. These and yeah, actually for the first one, I don't think you have to get rid of any extra cases. But yeah, just go ahead and do them.
I have a question for like the ways to roll the 7. Can it be a plus b plus c and b plus a plus c is another choice?
Yeah, if you switch if you swap the values, then that's counted as, we'll count that as distinct for this problem. Same goes for the second problem, of course. All right, so I'll go over these now. Okay, so I saw a lot of people got the first one. So if you think about it, it's just like a plus b plus c is equal to 7. And the restriction on all these variables, they must be between 1 and 6. Well, the thing is, none of for a plus b plus c equals 7, if we're just considering positive, there's no upper bound, then it's actually the same because, well, what's the biggest any one of these can be? If it's 1 plus 1, then the last one has to be at most 5. So we don't actually have to subtract anything. And we can just directly apply stars and bars on this. 7 minus 1, choose 2, is equal to 6, choose 2, is equal to 15. And if you want to derive this the same way you can, but in general, if like the number here is n and there m variables, then it's n minus 1 choose n minus 1. You can like draw it out, note, and see how why that is. For the second problem, I'll go over. I don't think anybody got it yet, although some people. So if you just blindly apply stars and bars, right? It's 3 positive numbers, sum to 13. 13 minus 1, 12, choose 2, 66. Okay. And I think some people got this answer. But the reason why this is wrong is, well, what if you have like 1 plus 1 plus, this counts 1 plus 1 plus 11, and that's no good for 10-sided die. So we need to subtract those extraneous cases. So sometimes we'll have to go into messy casework, but if you think about it for this, this is actually the only like extraneous sum there is, and it's orderings. There are 3 ways to order this because there are 2 1s and 1 11. So you subtract 3. So the answer for the second one is 63. Yeah. So I think you might start to be getting stars and bars a little bit after these. So yeah, we'll go on to the final stuff. So for in-class problems, how many ways can 12 pieces of candy be given to 5 kids? A 6-sided die is roll 4 times. How many ways are there to roll a 9? All right, so these are not like these are not very clear. So this is a total sum of 9. Okay. 12 pieces of candy distributed to 5 kids. I actually want you to do this both ways, both interpretations. So the total is always going to be 12 pieces of candy given. I want you to send me 2 answers. Try to get 2 answers to this problem. 1, everybody gets at least 1. 2, some may get none. All right. So yeah, send me the answers for these once you're done. Alright, so I've been seeing some correct answers for all of them, so yeah, I think, does anybody want to go over these last problems really quick?
Can I go for the first one?
Yeah, sure. Do you want to go over both parts?
Okay. So for the first part, we have 12 pieces of candy and we distributed to 5 kids. So there are 5 kids. Let the number of candy they get be A, B, C, D, and E respectively. So A plus B plus C plus D plus E equals 12. Remember, they're positive and they have no limits until 12. Actually, not 12, 8. So, using the stars and bars, we can find out that there is a total of 11 choose 4, which gives a total of 330. And the second part, we have 3, 4, wait, yeah, still the same problem, but one of them could be 0. So instead of A plus B plus C plus D plus E, we can make it to A plus 1 plus B plus 1 plus C plus 1 plus D plus 1 plus E plus 1 equals 17. So, still using the hockey stick I mean the stars and bars, we can, it leads to 16 choose 4, which is equal to 1820.
Yeah, that's right. That's the right explanation for both of these, how you transform the second one, how you do the first one. So yeah, I won't go over this one anymore. Does anybody want to go over the second one?
I want to.
Okay, sure, go ahead.
So for the second one, a 6-sided dice is rolled 4 times. How many ways are there to roll a 9? First of all, we decide to see if we can just use stars and bars immediately. So we pretend that 3 dice are 1, and the other dice is a number. So 1 1 1 would obviously mean 3, and 9 minus 3 is 6, so that's already in the limit. So it's okay. So we could immediately use stars and bars identity. Using this, A plus B plus C plus D equals 9, which is who wrote that? Which is a positive number. So using the stars and bars / sticks and stones, we find out that this literally leads us to 9 choose 3. Yeah, sorry, 8 choose 3. 8 choose 3. Sorry, yeah, 8 choose 3, which doing this question leads us to the answer, which is 56.
Yeah, that's right. I just want to mention something. So yeah, first always check if there's like any bounds you have to subtract on. That should be the first step you're doing. If not, in this case, that's good. But if you do, then you have to do something like, let's say one of these variables was more than 6, then you subtract 6 from both sides. Then it's like a minus 6 plus b plus c plus d is equal to 3. Since this is greater than 6, this is positive. So with stars and bars again, you do stars and bars on this, multiply it by 4, since it can be any one of the variables. 4 variables and then you subtract it from the total. Well, if you do that actually and you interpret it combinatorically, you'll get the same answer. You'll get subtracting 0. So yeah, that's what you'll have to do in cases where you have to get rid of things. In more complex cases where you have to get rid of things, you might have to use the principle of inclusion exclusion, although I don't think any of the AMC 8 problems quite get to that level. All right. So yeah, that's all for this lesson and all for the AMC class. And yeah, thank you for coming. I'll post the recording and then we'll have our final homework set out and I'll try to get a recording for solving those problems as well. And yes, this is the last class for the summer session. There probably will be a future session in the fall, but I'll send an announcement on that later during the week concerning that. And so yeah, with that, class is over.
Thank you.
Thanks. Bye.
Thank
Bye.
you.
Bye, William.
Bye. And yeah, there's no
Bye.
class next week.